If we're going to use computers in control, we must be able to take information from the real world and convert it into a form the computer can make sense of. When this has been done, we can analyse this information, we can display it, and use the computer to make decisions based on the data it has received. In this case, we're using 4 sensors and feeding the information into the micro. The program is continuously running in the microcomputer and sampling each of the outputs from these 4 sensors and displaying the results on the screen over here. Up in the top left, we have sound here, hello, and it's detected by a microphone here. Here we have distance, and we have an ultrasonic distance detector here. If I put my hand in, it will come down, and as I pull it away, it goes further away. Temperature is displayed here, and it's sensed by a temperature sensor here. And a light is displayed here, and as we shine the torch in, we can see an increase in light level. As I switch it off, it dies away. Well, in this program, we're going to look at sensors, many of which can be connected to a home micro. But first of all, let's look at how they're used in an attempt to solve a problem that's frustrated all of us at some time or another.
Traffic like this is a familiar inconvenience to anybody who lives in a large town or city, but to London Transport it's a real headache. They have over 6,000 buses running on 358 routes, and any stoppages cause their timetable to go haywire. The problem is that once a bus has left the garage, it's difficult for the bus inspectors and regulators to find out where it is and keep the timetable running properly. To help resolve the problem, London Transport has started to put microcomputers on board the bus. And fitted to this bus are a lot of sensors which enable London Transport to know what the bus number is and where it is. For example, these sensors underneath here enable the computer to detect bits of metal inside this piece of plastic. And so the computer knows that this is bus number 493. To see how this works, we visited the London Transport Research Centre.
Right, well, first of all, I'll drop the running number in so that the bus-borne computer can know which bus we are and what the duty is. Pushing the appropriate buttons.
It says 493.
Fine. The driver has a number of units available to him to be able to deal with the transmission of data and voice which goes to and fro the bus and the landside equipment. Data coming to him is translated by the bus-borne computer to show him text messages which are available on the display, and he can respond to those messages saying okay, yes or no. And on some occasions the driver wants to make a normal voice call to the regulator. There may be some accident he's seen or what have you, so he can request a call by touching the call and the send button, and the landside computer will talk to this little computer and sort out which channel he can actually speak on.
Obviously the thing you're really interested in is where the buses are, so how are those things sensed and what sensors have you got for those?
Fine, well, information is fed to the bus from the roadside, and together with other information on board the vehicle, a burst of data goes back on a regular basis, and if you looked at that little light, you'll see every now and then there's a little blip, and that shows that data is being transmitted from the computer through the radio back to the base equipment. But to know where it is, we use basically 2 systems. One is an electronic signpost, which is basically an aerial that's embedded in the road, rather like the sort that are used for traffic light priority type of systems,
right,
and entering into car parks. And the aerial transmits an electronic signal to the bus, which is detected by means of an aerial, which is mounted underneath the vehicle.
Right.
The information comes back to the computer, and so every now and then it gets an indication of exactly where it is. And in between the beacon sites, we use a nice piece of 1960s technology, which is used ordinarily on the bus to control the transmission. We tap into it and get a distance travelled signal, which is fed to the computer, and that information is transmitted via the data system.
Information gathered from every bus is transmitted back to the central computer. This displays a map which shows where they all are and what they're all doing.
Well, as the computer could track where the bus was from information fed back from its sensors, so we can keep track of where this buggy is from this sensor. It's a barcode reader, and it can detect the position on the black line. And there's another sensor here, which is a light detector, and it can tell whether it's reached the light over there after threading its way through the maze. John, it almost seems as if we could sense anything.
I think we can, Mac. I've even got here a Pong sensor. It's actually a combustible gas detector, but obviously is used for picking up gases and setting off alarms. We've got a whole range of sensors. These two are for detecting light. That's an analog sensor which detects how bright the light is and gives out a bigger voltage if the light's brighter. That, on the other hand, is a digital sensor. If the light is above a particular level, it will switch on. If it's below, it'll switch off. And this pair of sensors are for temperature. Again, an analog one. The more the temperature, the higher the temperature, the more the voltage. But this one only switches on at a certain temperature level.
It's like a house thermostat.
That's exactly what it is. We've got a microphone here for picking up sound. And got a whole range of position sensors here. This one is a tilt sensor. There's a blob of mercury in the bottom, and when I tilt the device up, the mercury moves down to make a connection between those two wires.
It doesn't detect the degree of tilt, just whether it is tilted or not.
Yes, it's just an on-off device. On the other hand, the joystick can be used to detect how far something has moved. That's just an ordinary joystick as on a standard games paddle on a computer or something. And here is a flow meter. As fluid flows through here, it rotates a vane and comes out, and as the vane rotates, each time it goes round, it produces a pulse, so you can tell how much fluid's gone through. That would be used, for example, in a car to determine how many gallons of petrol you'd used. And over here, we've got the ultrasonic sensors that you showed us at the beginning of the programme. That's just one sensor. But here, a pair of them have been combined, not to measure distance, but this time to measure movement. And if there's any movement in a room, that relay will be operated and it could sound an alarm. And another alarm device is this very simple device. It's just a pressure pad. When you stand on it, it closes a switch. This one over here is a fluid level detector. When the fluid rises, it closes a switch and could switch something off. You may have something similar at home, perhaps. Right, Matt, can you just bring your finger up to that sensor? Right. Well, you can see on that one, you don't even have to touch it. It's called a proximity detector.
So to some degree or other, all these sensors can replicate all the sense of the human body. They can hear, they can see, they can smell, and they can feel, and they can also find out whether you're in balance or not.
They can, and the common factor about all of these is that they produce a voltage which can be fed into the computer.
Can we go into a little bit more detail about the difference between digital and analog?
Yes, we've got here a simple setup. There's a voltage supply there for you and a bulb, and if you turn the voltage up, you'll see the bulb lights. And we've got an analog meter over here which measures the voltage across the bulbs. But as we change that voltage, we can monitor it also on a digital device. And over here we've got a couple of digital displays. Underneath is a meter, and we've hidden some of the numbers so that all you can see is either a 0 or a 1. And there's a light which is either on or off. And both of these change at 1 volt. So if the voltage is more than 1 volt, the light goes on. Now that is just using 1 bit, an on or off state, to measure the voltage. But very often a computer needs to know the voltage with rather more resolution. You need to know not just if it's above or below. And in that case, you need rather more bits to represent the voltage. Now, that device over there contains an 8-bit analog to digital converter and 8 display lights. As you change the voltage with that variable resistor, so you can see that more or less LEDs illuminate. And those 8 LEDs, those 8 lights, can be used to represent 256 different values. So with an 8-bit analog converter, you can represent 256 different values. Now, in the computer here, we've got a 12-bit analog to digital converter, but very similar thing. And there's a program on the screen for reading the values, the voltages that are fed in and displaying them on the screen. 10 says clear the screen and so on. But line 30 is really where it's all happening. It says print add val. That is the value of the analog to digital converter number 1, which we've got connected across the light bulb. So if I run that program, and you change the voltage slowly up, if you would. It's very small at the moment, and the voltage, or the numbers are increasing. Turn it right up now, Mac, and it's up to 65,520, which is, in fact, the biggest number that this converter can produce. But you'll notice they're just numbers. They don't actually represent a voltage. And if we wanted that instead to display a voltage or a temperature on the screen, we'd have to have, so to speak, a fiddle factor in the program. We'd have to multiply or divide that number to rescale it down to the correct scale.
Well, what we have here effectively is an analog to digital converter. In a real situation, the digital information is fed into the computer itself. The computer can then make decisions and send back information to keep in control. Today, wind tunnels are essential for testing the aerodynamics of many products, like this propeller made of a new carbon fibre. Measurements of the stresses and strains on each blade are recorded under a variety of different wind speeds which can be carefully controlled. The trouble is that the model has to be supported from the floor or ceiling, and the support can interfere with the wind flow, causing errors in the measurements. Peter Fortescue of Southampton University has come up with a different method.
We suspend the model magnetically. This model has a powerful magnet embedded inside it, and that is suspended within a magnetic field provided by the electromagnets in our tunnel here.
In fact, there are 8 electromagnets surrounding the test chamber. The strength of the electric current driving them is controlled by a mini-computer.
As you may know, if you suspend a magnet underneath another magnet, it will either fly up or drop out, and it's basically unstable in that sense. So we have to provide a closed loop round the system, so that if the model is, say, too high, then the magnet is weakened and the model will drop down to be in the desired position.
6 slits of light are projected across the chamber. As the model moves about in the beams, optical sensors locate its precise position.
If we look at one light beam, then the light beam, for example, is shining across the model, and the model will shadow a detector which is on the far side of the wind tunnel. These detectors will give a signal which is proportional to the amount of light falling on them. So as we shadow, a signal from the detector effectively tells us where the model is. That is fed back into the computer. It's fed into the computer and is fed back to the magnets to control the strength of the field in which that model is sitting. Now, we don't just have one single movement to control, the up-down. We've got to control fore and aft, left-right, as well as the 3 rotations.
Once the computer has complete control, the strength of each of the electromagnets can be varied to put the model through a series of pre-planned moves. As the wind tries to move the model, the computer adjusts the currents in the magnets to keep the model in place. The extra current needed is a measure of the wind's effect. Using the new system, magnets can be put into almost any model and tests carried out without the interference of the traditional supporting pylon. One problem there is keeping the model in one position and not allowing it to go into wild oscillations. John, could we go through the principles behind solving that problem?
Yes, Mac. We've got a similar sort of setup here, but with a table lamp. At the moment, I've got this photocell feeding a voltage into the computer, and the computer's displaying on the graph here the level of light landing on that photocell. And if I put my fingers in front and change it, you can see the level of light changing. Now, as well as that, we've got an interface box connected to the computer, and that interface box can, under computer control, turn the lamp brighter and dimmer. Now, at the moment, there's too much light landing on the photocell, and it's fairly obvious that to control that, you have to make a number of decisions. You have to set the target level of light that you actually want, and then measure the level of light that's actually arriving on it. Work out the difference between those 2 values, and then alter the output by the amount of the difference. And to keep the system running, you need to go round in a loop, repeating that time and time again. Well, let's run a program working on this principle. There's the light level. And you can see rather unexpectedly, the light is going too bright and too dim. And the reason for that is that the light bulb takes quite a time to heat up and slow down and cool down. And by the time it's done that, the computer has taken another sample and has tried to correct again. So there's a fundamental problem here.
So it's overshooting every time.
It's overshooting the whole time. So to get over this problem, you have to change the algorithm or the method of solution, and you have to introduce a couple of extra stages. At the moment, we alter the output by the difference of light levels. And if instead of doing that, you just alter it by a small proportion of the difference of light levels, it means that it'll gradually home in on the correct value instead of shooting towards it and overshooting. The other thing that's worth including is a step to ignore very small changes. So if you're pretty near the right level, then don't worry, just get on with it. Well, let's show that program running now. You can see the light level's far too high, and it drops down quite rapidly and smoothly to the correct level. And if I take the lamp and push it right down onto the sensor, there, the light level drops.
And there it falls back into place. Well, there is one piece of equipment which uses these principles, and that's this professional enlarger. There are 6 sensors in here which not only measure the light's intensity, but also the 3 primary colours, red, green and blue. That information is fed into the computer, and then the computer feeds timings to these electric motors up here, which move filters into position to get the optimal exposure.
We'll make another use of optical sensors is in a fog detection. We've got a setup here. The light shines through this gap to the photosensor, which is connected through the computer, and displays the light intensity on the screen. Now, if the light intensity falls below that level, 6.5, we're going to declare that as fog.
Well, Steve's made some nice 1953 vintage Hammersmith fog here, and let's see if it works.
Now, it's detected fog, and if the fog goes on for long enough, it's going to conclude, there we are, sound an alarm, and conclude that we have got something we'd better deal with. OK, well, thanks, Steve, for that. Now, there is one other situation that might occur. The equipment might go wrong, or you might get an obstruction in the way. If I put my hand in the way, you'll see that the light level goes down to 0, and on the screen, the computer somehow knows that there's an obstruction. Well, it knows that because we've set another threshold level, this time at 3.5 units. And so we're saying that if the level of light is between 3.5 and 6.5, then it's fog. If the level of light is below 3.5, then we've got an obstruction. So here we've set up 2 threshold levels.
And we could change those levels by simply changing a couple of parameters in the programme.
Very easily. Now, yet another use of optical sensors is for telling whether a shaft is rotating and how fast it's rotating. This sensor here, used on the buggy, emits infrared light, which is reflected off this silvered strip on the disc, and it's detected below. And so the computer can know from the obstructions how fast the shaft's rotating. Again, here, we've actually got a disc cut in half, which is cutting a light beam, completely cutting the infrared beam between there and there.
Of course, very often this disc is actually a complete disc with holes in it, so it can not only detect the speed, but it can actually detect the position of the shaft.
Yes, that's right, Mac, and recently I saw a hoist at Southampton University which used that technique. Chris Wortley has been working on a student project to improve this industrial hoist by adding a microcomputer control system. The only modification he's made to the hoist itself is to add a couple of sensors to the motor shafts to make sure it stops exactly at the right place.
Chris, what's the aim of this project?
Well, this is a third-year undergraduate project. The aim was to take a conventional hoist, a 1-ton hoist, and add onto it a cheap computer which could control its position very accurately without attempting to have the computer pick things up for itself, which would be a robot.
So what enables the hoist to know exactly where it is?
On the 2 movements of the hoist, the vertical and horizontal, there are optical encoders.
Now, what's an optical encoder and how does it work?
Well, inside each encoder is a disc similar to that. This has little black markers on it. As the hoist moves in either direction, the disc rotates and interrupts a light beam, which sends pulses back to the computer at high speed. These can then be counted up by the computer, so it can keep a continual reference in space of where the hoist is.
Presumably you've added some extra hardware to connect the computer to the hoist. What have you added?
There's several little stages to upgrade from the small power of the computer through transistors and relays up to the large mains power that the hoist has.
What are the major advantages of using a computer-based system like this instead of a hand unit?
The major use is that you can teach the hoist a set sequence of movement. The computer will be remembering the sequence, and then when you play it back, it'll repeat it exactly as it was taught.
Well, that's all very well, but the information from those sensors is straightforward ons and offs. The trouble starts when you want to digitize a complicated signal, for example, coming from a microphone. John?
Well, on the screen here, we've got a representation of the voltage you get out of a microphone plotted against time. It's quite a complicated wave shape. Now, if you sample that fairly slowly, using a quite slow analog to digital converter, you don't get a very good impression of what's really going on. For example, here, the computer thinks that for that period of time, the voltage is quite small, whereas in fact, the sound wave was going up to a very high peak there and back down again. If you sample twice as often, then you begin to get a much better representation. And in fact, here we're sampling at a rate which is twice the frequency of this wave. And there's a general principle that you have to sample at least at twice the frequency of the highest frequency that you want to get an impression of in the computer system. Now, you can sample even more rapidly, more rapidly still, twice as often again. And you might think, well, why not go always at a flat-out rate? Simply, it costs money to sample at high speeds. For example, on this computer system, there's an inbuilt analog-to-digital converter which samples 100 times a second, but quite often you need to sample more frequently. Now, you mentioned sound. Here's an unusual sound recovered from an unusual situation. This one, in fact, came down from a satellite.
And that, in fact, is every pip is one line running right across this picture of the weather around the British Isles. And at each point here, it's taking 8 levels from white of these clouds down to black of the sea. And we can see England here and Ireland over there and a rather nasty storm up in the north over here. You can actually produce a similar sort of picture on the microcomputer, a lot cheaper equipment than actually was used to produce that high-definition picture.
Yes, to get a picture at all from this tape, which, as you say, has lines on it, you need to sample about 1,000 times a second. So if we feed the signal from there through the interface into the computer and then show you a picture produced in that way, you'll see an image on the screen there. Now, in fact, we recorded this morning, and it appears to be raining or cloudy virtually everywhere. You can just see Italy and a bit of Spain down there. The quality leaves something to be desired, and it's a pity, really, we haven't shown you a better one, because you can produce some quite respectable images with this equipment.
Well, that was intermediate frequency sampling at about 1,000, but many people are familiar with this. It's a digital disc, and the highest frequency you're going to meet, or you can hear, is about 20,000 cycles per second. And on John's rough rule of thumb, on a digital disc, they're taking about twice that, which is 40,000 samples every second to get the high quality out of a digital disc.
Over here, we've got some demonstrations of very high-speed sampling. Inside a camera, there are a number of sensors, and as you can see, we've taken this one to pieces, and there is a lot of electronic circuitry in it. And in fact, there's one printed circuit sheet there, which we've spread out here, and there is a sensor here, a photo sensor, which senses the light after the shutter has opened. And that's connected to a high-speed analog-to-digital converter, and then through a microcomputer on this flexible board. And once the shutter's open, the camera decides how long an exposure it needs and then shuts the shutter at an appropriate moment. Now, we've got the same type of photocell here connected through the same interface that we saw earlier and through onto the micro.
That's a replica, really, of that circuitry, isn't it? It's a little bit bigger.
Yes, rather considerably bigger. But it does the same job in many ways. But this time, we can set it up so that we take samples of the light intensity landing on the photocell. I've got an electronic flash gun that gives a very short burst of light, but if I fire that above the cell, we'll see on the screen in a moment a graph showing the light intensity. I'll just shade it from the studio lights, fire. Now, when I fire it, the computer grabs 256 samples very, very rapidly, but then it displays them on the screen somewhat more slowly. In a moment, it's finished now.
And that's about 1 millisecond, a thousandth of a second that it's displayed there with all the sampling that's gone on in there.
Right.
That's beautiful. Well, we now know how a computer-controlled system can figure out what's going on around it. Next time, we'll be looking at how robots can be controlled when they're moving about. By then, I hope you've got your camera back together again, John. Goodbye.